Thank you. I would like to thank the organizers for the invitation to give this series of 2 lectures. It doesn't work?
No, yes.
Recording in progress.
Ah, okay. So it's going to be a series of 2 lectures on the realization of p-adic local Langlands for GL2 QP in the Drinfeld Tower. That's based on a joint work with Pierre Colmez and Colmez-Dospinescu. But the first talk to talk today is on cohomological foundations, which are needed for this work, and mostly it is about p-adic pro-etale cohomology, which is the key input. P-adic pro-etale cohomology of analytic varieties. So when we started this work, it's already, I looked up, and it's already like 9 years. And when we were looking first at the Drinfeld Tower, we really didn't understand p-adic cohomologies of analytic varieties at all. We were just making our way in the subject and trying to mostly guess what is happening. So now we understand it much more. So I want to survey what we do know. So let's start with a setting. I should advertise that actually everything I am going to say and a lot more is in the survey we put a couple of weeks ago with survey we wrote with Pierre on the archives. So you can look it up if you are interested. Okay, setting. So I'm going to work with rigid analytic varieties. And in general, I'm going to assume that they are countable at infinity, so certain computations work better. Then K is going to be complete discrete valuation field of mixed characteristics, so let's say over QP. OK will be integers in K. There is going to be a perfect residue field. And C is going to be the completion of an algebraic closure of K. And I'm going to denote by GK the Galois group of K bar over K. Okay. So I want to start with the first part of what I want to say are slogans. So this is, of course, very impressionistic. It's going to be just a list of slogans about the whole subject of computing pro-etale cohomology, of p-adic pro-etale cohomology of analytic varieties, the way we understand it now. Okay, so let's start with X over K, smooth, rigid analytic variety. First, we are interested in computing pro-etale cohomology of. So I'm going to look at the geometric one. So XC with QP coefficients. So first slogan is that we computed now. We know we can compute it now with various levels of precision using the Rom cohomology plus extra structures on it. So first of all, Hodge filtration. Maybe I just describe it this way. Well, maybe here I could put this. And then the hidden structures, so Frobenius, monodromy, and some residual action of the Galois group. Okay, so how does this go? So why? Or how? Okay, so let me start with the first step here, which is that locally for the etale topology, we have K par 1 lemma, which means that we can compute this pro-etale cohomology locally as the group cohomology of the fundamental group with QP coefficients. Okay, now we use mixed characteristic Artin-Schreier. Okay, so this is a bit abuse of terminology, but let me just use that. And then we pass from QP to some period rings. Now we have plenty of period rings you can choose here. So I'm just going to write B without referring to any particular one. There is some Frobenius hidden here, and also filtration actually. And this period ring is a perfectoid period ring. Okay. Now we have standard tools in modern p-adic Hodge theory. So we have almost purity here. Now, almost purity allows us to replace this complicated group by some gamma. And for us, gamma here, we are in the geometric situation, is going to be, it can be taken to be ZPD, where this is the dimension of our variety. And again, with the same, I still keep the period ring, B. Okay, but now I don't like this period ring. So I pass from this to, so this is the completion now. Another standard tool in modern p-adic Hodge theory. So the completion allows us to replace, so we still have this ZPD here, which is very good. And now we have another period ring, which is not perfectoid anymore. Now we use Lazare, standard theorems of Lazare, to pass to the algebra of this gamma with this very simple ring B tilde, and from here, where this Lie algebra is a Lie algebra of something like I mean, it's ZPD over there. My gamma is ZPD, so you basically have the RAM cohomology already here, and then you get all these extra structures from these constructions, from the period ring, Frobenius filtrations, etc. So that's the algorithm which, if you tweak it in various ways, you get a number of results which we use these days, and I will explain them later. But as a slogan, that's the picture here. Okay, so let's maybe focus a little bit more for a second slogan on this data here. So we have the RAM cohomology, and then we have this, so the RAM cohomology with filtration, of course, and these hidden structures, those are encoded in Hyodo-Kato cohomology. So we have phi n and this residual action, which comes from the potential stability phenomena. Okay, so what is the yoga here for computations? Is that this Hyodo-Kato cohomology behaves like etale cohomology with coefficients L different than P. And this can be made, so we think of this as an avatar of this cohomology, so kind of classical cohomology. And this can be made, in fact, quite precise in many settings. So for example, imagine that these are finite rank. Then both give rise to Veil-Delin representations, and they should be equal. So the Veil-Delin should be the same. But in the case of curves, analytic curves, of course, I mean, we made it, you can make it very precise, and you can, even though these guys are not going to be finite anymore, you have the same Veil-Delin representation plus actually the same action, the same representations of the orthomorphism groups of your variety. So at least in the case of dimension 1, you can make these things, this correspondence really precise. But the philosophy is this should be an analog of that. Of course, this goes all the way back to Fontaine and Illusi and to the algebraic setting. So that was the understanding. Okay, 3. So pro-etale cohomology encodes locally analytic phenomena, broadly speaking. For Banachian type of phenomena, you want to look at the etale cohomology of your varieties. And you have a natural map from etale cohomology to pro-etale cohomology. Now we know nothing about this map, so we don't understand this map. It's neither injective nor surjective in general. And what's the difference between this? So for practical purposes, for computational purposes. So here, so of course, if you are quasi-compact, there is no difference. But if you are Stein, for example, then you look locally here, and locally you compute with QP coefficients, so you can use rational p-adic Hodge theory. Locally, rational p-adic Hodge theory. So that's quite powerful, right? Well, here, what happens is if you are Stein, you still compute with ZP coefficients, and you invert your p at the very, very end. So locally, you still compute, even locally, you have to compute with integral coefficients. So you have to use integral p-adic Hodge theory. And maybe, because after all you invert p at the end, it suffices to do it up to controlled denominators. So this is much harder than this, of course. And maybe I have a couple of examples here. So for this point here, so example first, open unit disk over CP. So CP is the completion of QP bar. Then H2 etale is not 0, and this has something to do with CP being not spherically complete. And pro-etale H2 is 0, so the map is not injected in this case. But what we do use, so for the Drinfeld tower, we first try to get handle on that, or from p-adic Hodge theory, or from Breuil-Strauch conjecture, and then we pass to this, and this is done by, so for coverings of Drinfeld tower. So for coverings of the Drinfeld plane, let's say, we have that the etale cohomology. I write it in the derived sense, but it has to be understood on cohomology. You can you take pro-etale cohomology. You take G-bounded vectors, so the vectors which have a G finite G orbit, and you get the etale cohomology. Not in degree 2, just in degree 1. Okay. H1. Thanks. So this is one of our tools. So to sum up, pro-etale cohomology via these modern p-adic Hodge theory techniques now can be expressed using de Rham and Hyodo-Kato. Hyodo-Kato behaves like etale, so we can borrow results from a lattice situation and transfer them to Hyodo-Kato. And then all you have to understand is how this all plays together with the filtration on the de Rham side. And that brings you to pro-etale, and then to pass to etale. If you are lucky, like we were here, then you can do that. Okay. So that basically sums up all my talk today. Okay. Yeah? No, G is, sorry, this, G is GL2. GL2 QP for, sorry. It's not the Galois. Oh, they work actually. I thought they were broken. It's just Eugen didn't like them. Okay. Okay, so now I'm going to do the same, but much slower. I mean, now I'm going to, yeah, okay. What do I do? Maybe I just go with this. So I'm going to start with a very basic example. So 2. Example. All right. So open unit disk, right? So this is example we like to quote, that one and the affine space, which are basically kind of the same thing. So let's start with what happens over complex numbers. So open unit disk over complex numbers, dimension 1. So I think of this as an analytic variety, and we have the classical cohomologies. We have the RAM, C in degree 0 and 0 otherwise, and Betty cohomology with Q coefficients. We have Q in degree 0, 0 otherwise. And of course, we have the comparison theorem here. We have Betty okay. So these are our classical groups in this case. And let me just mention that there is a duality here. So we have HI DRAM paired with H2 minus I DRAM with compact support. I didn't list the compact support, so let me just list maybe quickly here the compact support versions. So HI DRAM with compact support. We have C in degree 2 and 0 otherwise, and Betty, same thing. We have Q in degree 2 and 0 otherwise. Okay, so we have dualities, which take the usual shape with usual numerology here. And the Betty one, same. Okay, standard picture. Now, having some basic computations in p-adic Hodge theory, we started to look at what happens for the p-adic unit disk. So now Y is an open unit disk, but now over CP, let's say. And now, of course, the DRAM cohomology is exactly the same. Has the same shape, both of them, in fact, same as above. Same as above, of course, C has to be replaced with CP. Now, pro-etale cohomology has the following shape. So Y, remember, is the geometric, so Y is over CP. So we get QP in degree 0, but then we get functions, regular functions on Y, modulo the constants in degree 1, and then we get 0 in higher degrees. And now the pro-etale cohomology with compact support, after we understood what this actually means. I will talk about this in a moment. Then this is 0 in degree not 2, and then there is an extension of QP by the functions on the boundary. So I will explain in a moment how we define them, modulo the regular functions. And so you have a trace map from H2. The trace map goes to QP, and the kernel is is this group here. So this is in degree 2, sorry. Okay, so just one more word about this, this boundary thing. So I will explain everything as I said. Yeah. So I sketched this thing, but now I will go through the whole thing and try to explain how this works. So we use we use computation comparison with the RAM and Hyodo-Kato. Yeah. So this chunk is going to come from the part of the DRAM complex, and Hyodo-Kato is the same as the classical cohomology, so it's 0. Yeah. Okay, so and the boundary fellow is just defined naively as regular functions on y minus z, and z inside y is quasi-compact. So this is what we call Gauss circle. It's in the setting we are working now, it doesn't really exist as of course as a rigid analytic variety, but all the cohomologies you will see when I talk about cohomology of these, I will mean in this sense. Okay, so this is done, as I said, using p-adic theory, but by the computations I will do later. But that's the final result. So just quasi-compact open. Yeah, sorry, quasi-compact open. Quasi-compact open. Aha. So let me make a whole bunch of remarks then about this. Maybe I put it here, the remarks. So first, so what's the difference between these two settings, the classical and here, is that, of course, these groups are now huge. So these pro-etale groups are large, so huge. Sorry, not a very scientific term. Also, well, I use just CP, but you can do the same computations, I think, with another bigger complete algebraically closed field, and you will see that, of course, it depends on the field now. So it depends on C. Okay, what about dualities? Here. So if you look at this picture, of course, you see some dualities. Of course, you can, I mean, there's QP here, QP there, but okay, well, it could be just a fluke, right? So who knows? But QP is in 0 and here and in 2 here, so it seems to match 0 and 2, so that's 2. But here, these two parts, so these two kind of the RAM parts. So this one is isomorphic with H0 y omega 1 by f goes to df. So that gives you omega 1 global sections of omega 1. And the other part, the boundary part, this is basically by definition of compactly supported coherent cohomology for partially proper things. It gives you H1. You have a sequence OY goes to OY of the boundary, and then you have H1 compactly supported. So these are in Serre duality. We are in the Stein. So our spaces are Stein, and for Stein spaces we have Serre duality in this p-adic context as well. So we have Serre duality over C. But now, if you try to do naive Poincaré, you have 0 matching with 2, and 1 here would match also with 2. So you have 3. So numerology for naive Poincaré, numerology doesn't work. So there clearly have to be there are some X groups hiding here, which one has to understand where they are hiding. Okay. So that's the main example I wanted to do, which kind of has basically all the phenomena which you see. The only thing is that you don't see Hyodo-Kato here playing any role whatsoever because of course this this space doesn't have really any classical cohomology, so you don't, and Hyodo-Kato captures the classical, so you don't see it. So I will give some other examples in a moment. Okay, so the third part is our main tool, which are the analytic comparison theorems. Okay, so here y is going to be now y over k, so it's going to be over k, smooth, rigid analytic. Rigid analytic variety. And I start with the first one, which we like to call basic comparison theorem. So let me state the theorem. 1. So we are assuming X is partially proper. So recall what it means. It means that you can exhaust X by a strictly increasing sequence of quasi-compact opens. Strictly increasing meaning that if you take a closure in the p-adic sense of the previous one, then it's included in the following one. N is smaller than R. And then we have an exact sequence of cohomologies. So we are looking at p-etale cohomology, geometric one still. And it's important to have this N and R in this range. And now we have two terms here. One is the Hyodo-Kato term, which I will explain what it is. And then there is the RAM term, which I will also explain what it is. The RAM term. So if you look at these computations here, everywhere there for the disk was coming from this term. And here on this side, you have the same thing, 1 degree lower. And then you have Hyodo-Kato again, 1 degree lower. Okay. Now what are these terms? So the Hyodo-Kato term is Hyodo-Kato cohomology, and I will say a few words about this in a moment. And then it's twisted by BST plus. In half of our work, we were working in the classical setting of functional analysis with locally convex vector spaces. Later, we work with condensed type functional analysis, but it really doesn't matter here because the spaces are very nice actually. And then we take n equals 0 and phi equal PR. So BST, let me just maybe I say a few words about the BST in a moment. Let me just mention what the Deram guy is. So the Deram guy is, so this one is very nice. I will say a few more words about this group in a moment, but these groups are really not too bad. And this is because we are working in this setting, partially proper. This one here we don't quite understand. It's completely derived, really. You take the RAM cohomology, the be the RAM plus cohomology, really. So you twist it with, yeah? X is equal, where is X? Where is X? Tensor product is over C and R in a moment. C and R, yes. C and R. And here it is over K because we started with K. And then we have FR here. So we take we take the Biederam plus cohomology really, but because we started from case just a twist of the usual Biederam cohomology, and we mod it out by the filtration, which is induced both by this filtration and this filtration here. Okay, so in the Stein case, we can understand this object quite well, and I will give simpler forms of these things for Stein. In general, for partially proper, we don't really understand these objects very well, so that's why many of our theorems are for Stein, but not partially proper. Okay. So, this is what I just said, like a moment ago. Sorry. So again, it can be exhausted by a strictly increasing sequence of quasi-compact open. So xi is included in xi plus 1 strictly if the Huber closure, compactification of xi is included inside of xi plus 1. Okay. Yeah.
Yeah, that the questions which you ask, they are all reasonable, but the answer.
Yeah, I want to keep it.
Yeah, but it's surprising. No.
What is surprising?
I mean, well, that this, I mean, it's just a case which, but it doesn't change the technology. But the answer you get, you have p equal to 2dr, so I mean, all the terms seem to really depend on r.
That's right. So you will get kind of a yeah. That's right. So there is bizarre shift happening, right?
Yes.
Yeah, that's right. But in general, for most of the computations, we just brutally assume R is humongous, like 2D or 2D plus something, and that's where we work with. But you're right. I mean, depending on what you choose, you are going to have different presentation of this.
Yeah, exactly.
Yeah, that's right. Yeah, no, that's right. We use it sometimes. There is a fundamental reason why we keep it, because these computations are done using symptomic cohomology, and what you just said is false for symptomic. Yeah. Okay, so let me just mention a word or two about these Fontaine rings here. So BST plus. Important remark. Maybe I should mention here, note that we are using the period rings plus period rings. We are not using B rings. We don't invert T here. So this is important. This allows us actually to, otherwise the computations I will be sketching later would just not work. So these are B plus rings, not B rings. Okay, and BST plus is just B Chris plus and one polynomial algebra in one variable. And let me just write this that way. And what do I want? Maybe just the monodromy. Monodromy is here minus du, I think, on this ring. So what I want to write is the fundamentally exact sequence here associated to that. So I have QPR, B Chris plus phi equal PR, or if you like, BST plus n equals 0, phi equal PR, and then Biederam plus mod fil R. This is one of our fundamental exact sequence in absolute p-adic Hodge theory, and in a way, this what you get here is some kind of a relative version of this sequence. Okay, now I need to explain this term here more. This one. So that's what I would like to do. Maybe here. Hyodo-Kato. So this is. Well, Hyodo-Kato is annoying, but the Hyodo-Kato isomorphism is really terrible. So this is a problematic. So for example, now after I don't know how many years of various comparison theorems in p-adic Hodge theory, so at least since the 80s, since the algebraic cases, we have a really nice proof of the de Rham comparison theorems. But everything beyond that, the potentialist, the semi-stable, the crystalline, it didn't get any simpler. It's still as complicated as it was before, and I think it's because of this horrible Hyodo-Kato thing. So let's look at Hyodo-Kato. So it is well, I shouldn't write, CNR vector space. And what is CNR? It's a union of, let's write it this way maybe, where K1 is an extension of K inside K bar. Module, so vector space, okay. And here we have Frobenius monodromy and this residual GK action. And we also have a Hyodo-Kato isomorphism between this Hyodo-Kato object over C and R with C and the Rham cohomology. So how do you access this cohomology? So outside the cases where you have semi-stable reduction and you can actually compute it maybe, and I will explain how. In general, you access it via the Rham cohomology. So if you understand the Rham cohomology, you kind of understand Hyodo-Kato at least as a vector space. And then you only have to figure out Frobenius and monodromy, right? But many proofs go by, for example, various descent properties of Hyodo-Kato cohomology are proved by descent properties of the Rham cohomology. You just use this. Okay, now how do you define this Hyodo-Kato thing to access? Yeah. Oh, these are just extensions in finite extensions. Okay, so let me say constructions. Sorry? Yeah. Yeah. So I don't know what happens really. I mean, we only have, so how does this fellow is proved? So you prove, I will sketch it in a moment, you prove a comparison between this and symptomic, but this comparison only works in a stable range, in this range, okay? So outside of that range, this thing cannot be computed using symptomic cohomology. So if you want to just accept that, then you can play tricks with the twist, because the twist here doesn't matter, right? In pre-etale cohomology, the twist doesn't matter. So here you can just play of course, with the twist, but then these two terms will change shape. So basically, if you want to study pre-etale cohomology with QP coefficients just by itself, of course you can, because the twist doesn't matter. But you will have to be careful what kind of formulas you get then. Yeah. Yeah, you have to define it. So in our paper we have to work to define it. Yeah. We have a definition in the paper which does it. You basically use the fact that these fellows are defined because of taking models. These fellows are defined over lower fields. Yeah. So the question about twist is actually important, because if you want to do the same for arithmetic cohomology here, you cannot do these tricks. So for arithmetic cohomology, this is really serious abstraction. For the geometric one, this is not really a serious abstraction. Okay, constructions. So of course, all of this, much of that anyway, was worked out in the algebraic setting first. And then Beilinson defined Hiodo-Kato cohomology very generally. And how is this defined? It is defined by taking, so etale locally. So I started with something which is smooth. If it's smooth, then de Jong tells you that etale locally on YC, for example, you have semi-stable models. So let's denote them by in this way. And then for these semi-stable models, you can just define Hiodo-Kato cohomology in the usual way, like Hiodo and Kato did. So that's a crystalline cohomology of the special fiber with lead vectors with some funny log structure, and then you invert P. So this is classical definition. And this allows you, of course, to see that because you are mod P, you have a Frobenius, and you have a monodromy coming from that funny log structure here. And the residual action comes from the fact that these models exist only locally, etale locally. And Beilinson developed what is called Beilinson basis to actually allow to glue these things. So this is the definition which works algebraically. And analytically, it's something similar. Again, because we are smooth, we can use Hartu and Temkin, and you basically do the same thing with the semi-stable models. So that works. Okay, now there is a motivic definition. So one uses Ayub's rigid analytic motifs. Yes, because I started from smooth. There's a paper of Baden-Snowden, which yeah, it's the same as here, because we start with smooth, then the etale is enough. Rigid analytic motifs. And in this theory, all these constructions here, so the singularization, alterations, semi-stable models, all of that is subsumed now in big black box. So we have super now nice black box, which puts all of these things there. So conceptually now, you can package all of that in the theory of motifs, and you get now, this was done by Binda, Galauer, and Vezani. You get a theory of Hiodo-Kato cohomology with all the operators for all the motifs, which recovers this construction, but also it can be applied. So advantage here now is can be applied to more general objects than rigid analytic varieties. So for example, perfectoid spaces. And this is useful in computations, of course. And here I run out of space. Maybe let me just finish on this side. So there is most recent approach for, it is Anschutz, Bosco, Lebras, Rodriguez, Camargo, and Scholze. So they developed the theory of the RAM stacks, the RAM Farc-Fontaine stacks, I think. Farc-Fontaine stacks. And this is going to recover Hyodo-Kato cohomology. And it also, like the point 3 there, it also can be applied to more general settings now than rigid analytic varieties. So also more general than rigid analytic varieties. Which is good. There is something else I wanted to mention here. Oh, sorry. Yeah. So conceptually, so this will bring me to the later point. So conceptually, what you are looking here at is pro-etale cohomology of these period sheaves B sub I, which are the relative version of the rings of functions on the basic affinoids covering the Y curve. Okay, so you're looking at this, you compute pro-etale cohomology, and we know that this is related to Hyodo-Kato. And I'll explain how, and somehow the curve approach, morally speaking, is doing that. Okay. Now I have to erase something, no? Yeah, I will talk more about this in a moment. In a moment I will. I have to erase something. Oh, this one is good. So later, in a moment, I will also talk about where the Hyodo-Kato isomorphism comes up and why it's so annoying. Okay. So maybe just mention one more. I have one more remark here that why this Hyodo-Kato part is useful, because it has nice topological properties. So this Hyodo-Kato cohomology, topologically, is a projective limit of finite rank vector spaces over this C and R. In fact, I mean, for much of the computations I'm doing here, you can just replace the C and R with C breviary if you are worried about functional analysis. And the action, so GK smooth, sorry, GK smooth. But here, using the C and R. Okay, let's look at some examples of computations. So examples. So as I said, maybe I should. As I said, this sequence actually is difficult to understand in the partially proper case because of this DRAM part. But in many cases, we can actually understand it. So first, the easiest case, when Y is actually proper, then the sequence splits. This sequence star above, there is some star there, splits. So what we get is the standard comparison theorem. So pro-etale, QPR, and now the Hyodo-Kato part and the DRAM part. And this is finite by Scholze, right? This is finite rank over QP by Scholze. So how do you split that sequence? So why does it split? So why? In this case, why does it split? Is because you see all of this as pre-shifts on perfectoid affinoids over C. And then you have here something which is just built from GAs, and this object here, no, sorry, the next object here which would be n plus 1 pro etale. Now this is finite rank, so you have finite rank vector space, so some C mapping to QP, but in this category, and then we know that this map has to be 0. So no maps in Banach-Colmez spaces. So this was the first application that we had of kind of geometrizing this comparison theorem. So if you leave this whole thing, this whole comparison theorem to this vector spaces V, capital V, capital S, then this map becomes 0 and the sequence splits. Okay, and now B. What happens for the affine space? Hn Hyodokato now, which compares with the p-adic is 0, if n is at least 1. And then Hn pro etale is the form that you probably have seen. So you have the differentials, kernel of the de Rham complex, and then there are some shifts, some twists. Okay, more generally, so let's miss, more generally, if y is time, what we get is HR pro etale, YC, QPR, and now we have Hyodokato part, and again we have this splitting. But now this is more subtle than in the proper case. So this exists because slopes of Frobenius are correct on the Hyodokato cohomology are correct, so are good. I don't want to explain that. But so you have Hyodokato part. Now this is completely classical now, and you have this analytic part which comes as a kernel. So we didn't realize it at the time when we were doing these computations, but we were extremely lucky. As I will explain in a moment, this completely fails for compactly supported cohomology. And traditionally, when people look at realizations of p-adic Langlands, they look at compactly supported cohomology, right? If we started to look at compactly supported cohomology of the tower, we wouldn't get this kind of things. We would get something that is much more complicated, and we wouldn't understand it. So it's good that we didn't know how to define compactly supported cohomology at that time. So. Okay. So let me sketch the proof of theorem of this theorem 1. So just the main steps. So first step, this is the comparison between what I mentioned, that we pass between pro etale and symptomic. So we have in our original approach, we actually used, the cheap way to define these passages via the original Fontaine-Messing map. So there is a Fontaine-Messing map, period map. So this was studied in the algebraic setting, but it doesn't really need it. So it works perfectly well in this setting. And it gives us a map from Fontaine-Messing symptomic cohomology to pro etale cohomology. Of course, Fontaine-Messing didn't really study it for rigid analytic varieties, but using Bellinson and ours approach, you can upgrade it. So you get this map, and how is this object defined? So this is very concrete. I will just write it in this way. These brackets mean a mapping fiber. And then we look at crystalline cohomology, absolute crystalline cohomology of of a hypercovering, semi-stable hypercovering on the generic fiber of YC. Semi-stable hypercovering. You look at absolute crystalline cohomology, then you take phi equal PR eigenspace, then you take a canonical map into crystalline cohomology, mod the filtration R. So that's Fontaine's messing, more or less, a bit change. No. Mm-hmm. Yeah, I don't care. Sorry? What is annulus? What pieces? Any R here? Yeah, so semi-stable over C just means it comes from a semi-stable from some level, basically. No, open ball is not semi-stable over C. Sorry, no. Sorry, yes. No, it comes from a semi-stable over something. Yeah, it's no, we don't allow formal. Everything is p-adic. Everything is, yeah. Okay, so how is this map defined? So maybe let me just mention how is this map. So this is defined using symptomic pro-etale side, symptomic etale side, sorry, etale side, and the key input comes from of course the key thing is the fundamental exact sequence in this side, so the relative fundamental exact sequence, FR B cris plus phi equal PR. Sorry, now maybe I don't want to do that. I want to write it this way: phi minus PR B cris plus. But you know, as a sheaf version on this side. So they were using that fundamental exact sequence, and so in the algebraics, right. So you prove that this is quasi-isomorphism. Did I state it? I didn't really state. This is quasi-isomorphism after you truncate at R. So up to degree R cohomology, these two things are the same. And the original proof. So we couldn't use the algebraic proof of Tsuji and Hyodokato Tsuji, the whole Japanese school here. So let me just mention why not. So in the algebraic proof, which was modification of the algebraic proof was modification of the original Blockato approach. So the algebraic proof, meaning in the algebraic setting, let's say the final version was due to Tsuji. So that uses Milnor K-theory and symbol computations to basically filter both sides by symbols, and then there is this Milnor K-theory shadow here, and prove that that all of these groups are the same. So we couldn't use that. So what we do here is we deform this map in the derived category, so everything works fine. Deform into this map alpha as in the slogan. So basically, you replace what is here a crystalline computation with this, which is basically phi gamma module computation. Phi gamma modules over various rings. Okay, so this was first step. The second step. Okay, so So what did we do? We replaced this proetale here with a mapping fiber where this guy looks like some eigenspace of crystalline cohomology, and this is crystalline modulo filtration. Now this object is easy. This we knew forever that it was easy. So step 2. Step 2 is to understanding these two objects. So A is the keynet formula for this object here. But now recall, we know, at least since Beilinson, so Beilinson observed, since these objects in these hypercovers are semi-stable, so they are local complete intersections, and Fontaine tells us that crystalline, Fontaine and Bad, I guess, not Fontaine, sorry. Beilinson and Bad, they tell us that crystalline cohomology for local complete intersections is the same as derived de Rham cohomology. And now, once you formulate that, all these formulas which appear in the papers of Kato, Hyodo, Tsuji, etc., make complete sense because now we just compute with derived de Rham cohomology. So if you do that, so let's pretend, so let's assume this guy exactly comes from K, so there is maybe some C here. So you have Y over some K cross C, right? And now this is derived de Rham cohomology. And now there is a keynet formula. And so you are looking at the Rham cohomology of Y itself and the derived de Rham cohomology of C. And Beilinson tells you that this gives you the period ring, P de Rham plus. So we have a formula for this. Of course, you have to do all of this modulo filtration level because this comparison I just told you, it only happens for Hodge completed cohomologies, so you have to mod out by some filtration level. But then you get that you have the Rham cohomology of Y, and then B de Rham plus, and maybe here I become solid to please Jean Hui, and then FR. Okay. So this we understood for a long time. Now this one here. So this is what we call Hyodo-Kato rigidity, the first term, and that's really annoying. So you look at this object here. Now it has a map to Hyodo-Kato cohomology of YC. At least if you think just about having semi-stable model, then this is just looking at reduction, sending P to 0 or something like that. There is an arrow. But now, if you look at Frobenius here acts by, it's an isomorphism, quasi-isomorphism. And here on the kernel is going to be highly nilpotent. And so you can use the work tweak, the work streak to actually get a section. And this is the most terrible thing in the whole theory. But it allows you to write now this as Hyodo-Kato cohomology, tensor BST plus, and n equals 0. And this is where our sequence comes from, basically, the fundamental exact sequence from this comparison, which is obtained by these slogans, and then identifying this, which is easy, and identifying this, which requires more work. Okay, so that's the basic guy. Now we have to derive some consequences of this thing, because by itself it doesn't really say anything. Okay, so let me mention one more thing, which I have here. So there is a computation in this first part, this identification with symptomic cohomology of Fontaine-Messing, which is key. So let me just describe it as proetale cohomology of period sheaves. So key argument in the proof. So let me state it as separate theorem, because since proving this, we actually use this in several places. So now I, let me describe what these I's are, is a compact interval, rational endpoints. And so this theorem concerns cohomology of the sheaves B sub i's. So Bi is a sub I is a ring of the basic affinoid on the Y Fark-Fontaine curve. You can make it into a sheaf, and the question, the computation which we have to do, is of cohomology of Bi, and this turns out to be the same as Hiodo-Kato cohomology. There are some twists, and B sub I and log. So I mean, we also want to deal with monodromies, so we attach log 0 solid CNR. Do it that way, and then I have to be careful here. We have the de Rham complex as before, P de Rham plus mod filtration, but now there are going to be several copies indexed by, let's call it Zi, and this is the set of zeros of the parameter T on SPA B sub I. And this cannot be on the nose. We know that all this needs truncations. Okay, I think I put all of this. And what's the difference between this and the previous thing is that here we do not take phi eigenspaces. We actually prove this phi equivariantly, of course also Galois equivariantly. So you get this formula for the cohomology of these period sheaves. So why do we care about this? So let me explain. Let's look at an example where T is a unit in B sub I, for example. Then all we get is that the pro-etale cohomology, where it's C B sub I as a sheaf, is Frobenius equivariantly the same as Hiodo-Kato cohomology. There are some shifts here. I don't know whether I got all the twists right, but now we are saying that we can recover Hiodo-Kato cohomology from the cohomology of the period sheaf Bi. So this is useful for us, for example, when you try to compare Hiodo-Kato cohomology on the Lubin, Tate, and Drinfeld sides. Hiodo-Kato cohomology doesn't make sense on this perfectoid tower at the end, at infinity, but this guy makes sense. So we use that guy as an avatar of Hiodo-Kato, and we flip-flop Hiodo-Kato cohomology. Okay, and you can derive something about the cohomology of the period sheaf B de Rham plus from the same computations. You get that pro-etale cohomology of the sheaf B de Rham plus now is the same as F naught de Rham cohomology and the sheaf B de Rham over K. So again, you will recover filtration 0 of this B de Rham cohomology from B de Rham plus the sheaf, the cohomology of B de Rham plus. Okay, so one thing you should notice here is that we get Hyodo-Kato from B sub I, which is what we wanted to have, but we also have this Derham junk here. And at least if you're interested just in Hyodo-Kato, it does look like a junk. On the other hand, this junk is kind of controlled, the T torsion here, so this is T torsion, but the T torsion is quite controlled. And let me make a remark that this can be untwisted from the left-hand side using L eta T operator. So this was done by Bosco. Can move T torsion via the L eta T operator to left-hand side. And then you have really nice formula where you put something like L eta T here, morally speaking, and you just recover this without this part. So this is useful for integral computations. But in our proof, we were, and later on, we were in duality theorems. We were basically using this thing. So let me make one remark. That everywhere here I assume partially proper, but this actually works also for quasi-compact, for example, this computation. And if your Y is equipped with an continuous action of some group G, for example, profinite, then what you get is that here you get a smooth action, and here you get a locally analytic action. So you see that this action is locally analytic, and this recovers the theorem proved by Gabriel and Juan Esteban. Okay, so maybe that was enough about that part. So I mentioned that we have this basic comparison theorem, and you can compute examples from that. But for real computation, this theorem is not enough. So you are trying to prove something stronger, to understand it better, and this is what we call CST conjectures, because they look like the algebraic CST conjectures. For algebraic schemes. So let me state this next. So CST conjectures. So what we had in these computations with symptomic cohomology was this Hyodo-Kato object. Tensor, I will skip maybe the decorations. BST plus n equals 0, phi equal PR. And then we had the RAM part, be the RAM plus mod filar. And this was basically definition of what one calls Bloch-Kato symptomic cohomology. And now we know this one computes at least in stable range. I missed twist somewhere here, twist. Stable range, pro-etale cohomology. So we have this sequence, but this is really not enough for computations. So what we do is we also have a map here, the Hyodo-Kato map, which goes into the RAM complex, with the RAM plus cohomology. And then, of course, this is canonical map into the quotient by filtration. And here we have filtered part of the RAM object. And here you have a you have a map like that. So now you translate it into, so pass to cohomology. The question is, can we compute cohomologies from this diagram? So what we get here is, I shifted and use this comparison. I get pro-etale cohomology with twist. Then I get this object x, Rn, and dr. So this we have seen above, the top guy, x and minus 1r, I think, and dr and minus 1r. But now I also use these maps lower. So here is a Hyodo-Kato, and now this goes into, Hyodo-Kato goes into the Ram cohomology, tensor B the Ram plus. But here, this is the same fellow. So this is just the same object. Here is also the same object. Here again I get the Ram cohomology, but degree lower. And that's about it, right? No. Yes. And here I get Hn of the filtered Ram of this filtration R. This is our sequence here. Did I do it correctly? Oh no, I confused this. There is no error like that. Sorry. Sorry. It's just this one. Just this one. Okay. So the natural question is here you have the same objects. Natural question you may ask, is this actually a bicartesian diagram? So you can formulate conjecture. This diagram is bicartesian. Right? So what does it mean? It means that if you look, if you get short exact sequence, which starts with this fellow, then you have sum of these two. So you have this guy, sum of these two, and then this guy. And this sequence is short exact. So you have that this pro-etale cohomology can be recovered from this filtered object, the Hyodo-Kato guy, and the Ram guy. So it would be great if this were true. I still have to understand this derived object, but still it would be great, but we don't know that. So it remains a conjecture. We were not able to prove it in general. But we know it, so known. Known for Stein. Known for proper, of course. And analytification of algebraic varieties. And now products of those. Also those, I think, where we assume, where Hyodo-Kato cohomology is of finite rank, maybe. So Hyodo-Kato is of finite rank. We also know it in this case. But we try very hard to prove it partially proper, but because of not understanding the coherent cohomology of partially proper varieties, we actually constantly were bumping into Arlin problems and failed so far. So at this moment, I'm not sure how positive we are this is. So for example, we proved it for products. So product of proper, for example, and Stein. And so you can naturally ask, is it true for what is it called, holomorphically convex analogs in p-adic geometry, which is like a fibration over a Stein curve with proper fibers. So a natural one step up from proper cross Stein, and we couldn't prove it in that case, so I don't know. But let's say you have it like in these cases, then this conjecture has second part, which follows from the first part, in fact. So, which when we computed it, it seemed to us super bizarre, because this second part tells us that we can recover the Ram cohomology. So for example, assume that you are Stein, but your de Ram cohomology is small. So you're like an interior of an affinoid or something like that. Then your de Rham cohomology is finite rank. But your pro-etale cohomology in this case is going to be huge anyway. But then still you can recover that de Rham cohomology, that finite dimensional vector space with filtration, although it's going to be kind of trivial in this case, from the pro-etale cohomology. So theorem, assume CST, then home from pro-etale cohomology to the period ring B de Rham recovers the dual of the Rham cohomology plus the Hodge filtration, and this home has to be Galois equivariant. And you can do the same for Hyodo-Kato, the same object here, and period ring BST, and you recover Hyodo-Kato, again dual, plus Frobenius and Galois action and monodromy. But here you have to be careful, there is some potentiality going on. And limit over finite extensions of, okay. So we found it super bizarre. Also notice that there is some compact support happening here, which we didn't quite understand. Okay, what else do I want to tell you? I need to get to these things. So I stated this conjecture, but actually it simplifies in the Stein case. The Stein case was the one we needed for the work on p-adic Langlands. And in the Stein case, this is called fundamental diagram. In our papers. So Y is Stein. And now we can really simplify it. So we get pro-etale cohomology. And then we get this Hyodo-Kato chunk here. So let me just spell it out. Hyodo-Kato n equals 0, phi equal PR. And the kernel is the these differentials. And now here you have, because you are Stein, so the Rham cohomology is computed by the Rham complex on the nose. You get a diagram like that. Which probably looks familiar to people who work on things related to Breuil-Strauch, and this was our main input, as you will see tomorrow. So I have a few minutes left. So let me mention what happens in the compactly supported case. So first of all, it took us a while to realize how to define what's a good definition of pro-etale cohomology with compact support. So let me just mention cohomology with compact support. So I'm going to always assume that Y is smooth and partially proper. Then our definition is that the pro-etale cohomology with compact support is just, well, this is hindsight, okay? So this is not the way we defined it, but in hindsight it's just a Huber cohomology with compact support, but etale. So in partially proper case, what it is, this is the definition we were always taking. It's just Proetal cohomology of the whole space. Mapping fiber of the map from Proetal cohomology of the space to Proetal cohomology of its boundary. And boundary is understood in the sense I sketched at the very beginning for the open disk. So you just take colimit over all the quasi-compact open of Proetal cohomologies of YC minus this. Okay, and then what do we know for this definition? So why did we decide this was the good definition? Because it satisfies the duality or we could guess at that time that it satisfies the duality with the usual Proetal cohomology. If you try to do it the other way, I mean, with the obvious way, you are getting something which is actually dual to Proetal cohomology, it seems. Okay, so basic comparison theorem still holds. So this is fine. So you can actually compare with symptomic, then compare with the Ramel stuff. But now if you want to proceed, there is no fundamental diagram. So we are talking about Stein case now. No fundamental diagram at all, and this is because Frobenius doesn't cooperate here. Frobenius has wrong slopes. But sometimes Frobenius is okay. So if Frobenius has good slopes, so if Frobenius behaves, then you have the fundamental diagram. Fundamental diagram is true. And this is the case, for example, for the Drinfeld space, probably for all period domains, p-adic period domains. For Drinfeld space, certainly. And then you have just the usual fundamental diagram as before. So let me just finish by stating an example here of computation of the compactly supported one. So Y is the affine space. Then we get HIC QP is 0 for I smaller than D. Well, that's always true for Stein. And I larger than 2D. That's also true. And then in degrees in between, I don't know whether I got the twists right, I hope. You get compactly supported cohomology. So compactly supported coherent cohomology is just in degree D because we are Stein. And then we have I minus D minus 1 differentials modulo kernel D, ker D. And this is between D and 2D minus 1. But in the final degree, there's one more degree. Did I don't put it here? One more degree. And this is typical what happens now. We have exact sequence between H2D, QPD. We have a trace map, QP. So this QP comes from Hiodo-Kato, and again it behaves just a ladder, so it is the good thing. But here you have an object which looks like that: HDC YC omega D minus 1, and then kernel D. So you have an analog of these omegas which appear here, but now you have compactly supported omegas. And this is the cohomology in degree 2D of the affine space, compactly supported. Thanks.
Thank you. Any questions? Actually, I have one, very naive. Sorry, does quasi-compact implies partially proper? Oh no, yes. If you are just quasi-compact, are you partially proper? No, okay.
Partially,
okay, well, sorry, yeah. Just wanted to clarify this.
No, we in our, Stein in our definition does not include
Stein, I know what it is.
No, but I mean it does not include affinoid.
Ah. Oh,
Because
so it's not
sometimes people say Stein.
I know this. I see. Okay.
Yeah.
Okay, thank you.
For Stein, you have an increasing sequence of affinoids. For partially proper,
the density statement on the global on the restriction maps, right? There's a density. The restriction maps are dense.
Right.
Not just
No, but they are affinoids. But for partially proper, they are quasi-compact. So, for example, proper is partially proper, but it's not.